Okay, guys, so rare chance to start on time today. How's it going? So good. I hope you enjoy your long weekend. So I definitely enjoyed mine. So I even forgot to assign the quiz. So I'll do it today. But yeah, with the amount of snow we had, yeah, you need to have fun. Hopefully skiing. Okay, let's try to get back to this to the operating systems. I will start over slightly from the boot sequence just to make sure that we remember what's going on. Otherwise, I think that there is no chance, right? After whatever, like a really nice weekend. What we're doing right now is we're discussing how to boot into main. So essentially, we talked at a high level about what pieces of firmware are running on the machine, how everything gets initialized. But in the end, what we as system designers care about is that the very first time something what runs before us gives us a chance to run, right? And in case of this classical boot protocol, BIOS loads the boot sector into this 7C00 address, jumps to the entry, whatever, the 7C00 address itself, starts executing, and this is where we start running, right? So essentially, if you like, all this Intel management engine was initialized, the system management mode as well. But in the end, we find ourselves running right here, this very address, right? And this code, we as system designers actually control this code, right? So we can in the x86 source tree, if you take a look, you will find this the source code, the assembly code of this boot block, right? And this is exactly 512 bytes. It's loaded by the BIOS, something what runs before us, loaded from the disk, and we are right here, executing the very first instruction at 7C00, right? And this is, let's just kind of talk over it again a little slower. At a high level, our goal is to reach the main function. It's our safe, kind of everything is C here. From this point, we just write regular C code and we will be building the kernel, right? So it's from there, like we shouldn't be scared of anything because it's almost like regular programming, right? Okay, so what's inside this boot sector? So again, we control it, and it's inside the x86 distribution. It's inside the boot asm.s file. And the very first instruction we execute is this CLI. CLI is an instruction which disables the interrupts, right? So since we didn't set up the interrupt descriptor table, I mean, we don't even know what it is, right? We'll cover it later, but to make sure that no interrupt arrives, no interrupts are delivered by the hardware, we just disable it, right? And our high-level goal after that is to say, look, since we're not exactly sure what was happening before us, and our high-level goal is to enable segmentation. And if I ask you a question, so why do we even need segmentation? Like, what are the steps which we need to do to initialize our execution environment on the machine, which has page table, segmentation, stack? Why do we need segmentation to begin with? Anyone remembers? Each process will need to have its own virtual memory space, and that's partially correct, because in the end, what we'll end up doing, we will give each process its own page table, right? We cannot enable paging without segmentation, but at the very early stages of boot, I just wanted to make sure that it's clear that we need segmentation for what reason. I can ask you differently. So in what mode of execution we're running? Exactly. So we're running in 16-bit mode of execution, which means that we only can reach up to 64 kilobytes of addresses, right? Because that's how much you can encode in 16 bits, right? Literally, our goal is to load the kernel from disk. Most of the memory below 64 kilobytes is taken by the BIOS. There are some holes, but not big. Essentially, we need segmentation just to make sure that we can switch from 16-bit of mode of addresses to 32 bits, right? At this point, we will be fine. We will reach the entire 4 gigabytes. And hopefully, in case of x86, it's true, it will cover all available physical memory. On real operating systems today, we probably will switch to a 64-bit mode of execution to make sure that, yes, we have larger memories. But that's essentially the goal. So we first switch, we enable segmentation to make sure, or so-called protected mode of execution, to make sure that we have 32-bit addresses. And what we do here, we specifically set a specific bit in this control register 0, right? I'm not I don't want you to spend a ton of time reading about those registers. There are 4 control registers on Intel, at least that I remember. Maybe there are 6, and they have various bits. You don't have to bother to remember all of them. Just remember that one of them has the flag which enables protected mode, and another one, CR3, which is important. We keep coming back to it, points to the root of the page table, right? So we'll use it in a second. But essentially, what happened here is we said, okay, we will load the pointer to the global descriptor table into we use this specific instruction load GDT. It's an Intel instruction. It loads this in a specific format, this descriptor, into the global descriptor table register, right? Yet another register which points, roughly speaking, to the root of the global descriptor table, right? And after that, we say, look, we enable long mode, and the next things we do is we long jump, saying that we'll be running in a 32-bit mode of execution, and our code segment will be this number, right? So after that, okay, segmentation is enabled. And again, we can spend more time on this, but on the other hand, your next homework will have a specific detailed step-by-step description. I will ask you to do the same, just maybe jump to 64-bit mode versus 32-bit mode. And the idea here is that at this point, the segmentation is on, and the address space which we configure, we said, okay, since we control the global descriptor table, we'll set up both the code and the data segments to start at address 0. So essentially, the base of the segment is 0, meaning that nothing gets added to the address. And the limit of the segment is 4 gigabytes. So allowing us to access the entire 4 gigabyte address space, right? At this point, if we have a machine with 512 megabytes, we can issue any load or store anywhere in this address space, right? So, and that's fine. So the way we configure the segments is we use this assembly macros, and it's this is part of the bootasm.s file, still part of the bootloader. We haven't even reached the kernel, and essentially this is how we define the global descriptor table. And you can, here it looks a little cryptic, but you can actually. And maybe the way I would write it is, you can, technically speaking, say, look, instead of using this assembly magic, I can just use the C file, something.c, and just declare a data structure which describes this guy, and the array which describes those 3 entries, compile it in C, and then link against the assembly code. Right, so those data structures can be safely declared in assembly. The authors of x86 choose to use assembly macros. We can scroll through the Git history, try to understand what was the logic, either the idea that illustrate the power of assembly macros or something else, or maybe it was easier to write at some point. But I think it's arguably you can write it in C. Is this clear? So you don't have, the point here is that you don't really need to use assembly as long as you can use C. So for example, C obviously doesn't have a long jump. I don't think you can issue a long jump instruction. So, but you can, for that, you won't need assembly, right? Or if you need specific control over the registers, for example, here, when you say, look, I want all these registers to be zeros, essentially, I first XOR AX, which is a 16-bit version of the register because you don't even have the 32-bit version, and then load those zeros into the data ES and SS segments, right? So for this, you need assembly. But for the data structures, you can use C. That makes sense? So it's a design choice, but I just wanted to make sure that, I mean, you don't have to take this code for granted. So like try to question what is written, and you say, look, I don't really want to write it this way. So can I write it in C, or can I do something else? Okay, that's totally fine. Any questions about this for now? So this is just like 2 slides to enable segmentation. This one declares the global descriptor table. The other one loads it into the local, the global descriptor table register, and then we do a long jump, and after that we're running in long mode. Okay, and what's our next step? Okay, we enable segmentation. We can access 4 GB of the address space. What did we do next? Do we remember? It's a bootloader. Yeah. Setting a stack, right? So exactly, we will set a stack. Why? Do you remember? Well, who remembers why we need the stack? Yeah, we just want to start writing C code. In order to write C, as I keep saying, the runtime of C is really like thin, right? So it's just the stack. So essentially, we need to do this to have the stack to make sure that we can call it to the boot main function. And this boot main function, we want to write it in C. Again, we can write it in assembly, but it's harder to read, harder to maintain, or easier to make an error, right? So the faster you switch to a better language, the better, right? So in this version of the kernel, they switch to C. You can very well try to switch to Rust as well. There's a repo online, which I advertise, which you can take a look how to boot into Rust. Okay, cool. So we have the stack, and we cheated a little bit. We said, okay, look, we will just use some random address in the address space to use it as a stack. Again, remember, the stack is just something what is pointed by this ESP register. And so what we did is that we said, okay, like if this is where the boot sector was loaded at 7C00, we're kind of guessing that nothing useful is there. I mean, we're not really guessing. We just carefully read the PC specification, and like we understand that those addresses are available. Maybe there is some like custom hook on this machine and something is really there, but it's kind of highly unlikely, right? And so we said, okay, ESP points just here, and it will be growing down from this address 7C00, right? So the very first push instruction will use the 4 bytes. If you're pushing the integer, which is 4-byte value, we'll use the next 4 bytes down from that stack, right? Make sense? So it's like, okay, cool. And at this point, we say, look, we can use a call instruction and jump into C, right? And this C code, which we're using, we say, look, we will be very, very careful. It will be just not a lot of code, and we hope we will fit into 512 bytes. And remember that x86 uses this Perl script to check. So here I can remind you, in a make file, what they do is that they say, when we compile the boot block, we'll just make sure that it's less than 512. For that, they use this tiny Perl script. And that's in case, you know, C compilers change, they did something wrong, and the code doesn't fit into 512. I, for example, myself had a bug here. So once I decided to tweak x86 in some specific manner, I don't specifically remember what I was doing, but I said, okay, I will put more functionality into this into the boot block, and okay, that script caught my error, saying, okay, you created a boot block which is larger than 512, so like please don't do it, otherwise we will later on crash anyway, because only 512 bytes will be loaded by the BIOS, right? And so this the C code says, okay, look, hopefully people who started the homework, well, now will be more familiar with this, but the idea is that they say, look, we're trying to read the ELF file from disk, right? And so we will use these definitions of those ELF header and program header, and we say, look, we will allocate some scratch space. We will say, look, again, some random address in the address space where we first load like the elf header and say, look, just to take a look what's there. We don't even know what's on disk, right? So we use those helping functions which go to the disk and read 496 bytes from disk. And we check, okay, we read here, we read this in this address, and we say, look, is it really an elf file? So is it really contains, does it really contain the elf magic? And that's very similar to what we do in a homework. We check for the elf magic and we say that yes, if it's not an elf magic, we'll return here, okay, like, you know, your boot is done, so you cannot boot because you don't have the kernel at this point. Okay, hold on. That's a great question. So read SAT, is that the system call which reads the data from the disk? Who can tell me? Correct. So what you're saying is that there are no system calls. Machine is ours. It's empty. I mean, maybe there is some garbage which was left there by the BIOS, but there are no system calls, right? So everything what we want to use either has to be provided by the hardware, partially by the BIOS, but we don't really touch the BIOS a lot. And so we have to write this function. So this function is written in this 512 bytes, which we're using right now. That's the only world we know. It's kind of important to understand that we only have this 512 bytes, nothing else, right? So what we're doing here is that, let me scroll here. I mean, maybe I skipped specifically this function. Let me just very, very quickly go to the source code to show you. And it's at this point, I mean, the beauty of this class, I keep advertising the beauty of the class. Yeah, at this point, we hate it. The point is that you can look at what's going on. So the way to go about it, you say, look, boot main.c, and you say, okay, what is that? What is it we're doing here? This is exactly the source lines which I put on the screen, right? So maybe module has some minor changes due to the version, but it's like, so essentially we say, okay, read SAC. Okay, cool. Let's read, what is this? Okay. I just search in that file, and this is the implementation of this read SAC function. I don't know if you see it, but yeah, it's small, large enough. So it says, okay, look, I do some magic converting the addresses, but really my low-level implementation of reading from disk is this read sect, which is reading the sector from a disk. If I go to this function, which is, I will search for it again, read sect. So it's implemented right here, right? So right above. And it's a very simple function. So at this point, what they do is that they say, look, if we believe that machine has a disk attached, then it must implement this low-level interface, which we will be using. Internally, this out byte instruction is, I don't know if they have it here, out b. Let me just see if they have implementation grab. What I'm doing, I'm searching for implementation of out byte, and I'm using this. Let me quickly maybe make, so this may clean the kernel just to make sure that I have less files, and I will search grep again. And now, I would guess that the way they implement it is that they just have this. So they define an inline C function, which internally uses an inline assembly, right? And this inline assembly literally just, I mean, I don't know if you're familiar with this inline assembly syntax, but roughly speaking, it says, okay, generate me this assembly instruction, and I take the argument 0 and 1, and this is in data and a port. But literally speaking, it's just the out B instruction. This out B instruction, Intel CPU takes it, and instead of like, what happens next? It sends it to the disk. So really, there is a specific specification which describes which ports connect to which physical hardware, and this specific port reaches the hardware of the disk. The disk itself has a tiny microcontroller. It senses that, okay, someone does this read, and it reacts to it and places the data from real spinning disks to the memory where we instruct the read to be performed. Make sense? Right? Any questions about it?
During loop loading, we're using this function that's
Why what? Yeah, because machine is clean. So we only can count on what is provided by the PC, which is personal computer, I think, specification, right? And this PC, when you boot on ARM, the environment will be slightly different, right? On RISC-V, slightly different. On Intel machines, which implement this PC specification, we know that the disk, as long as we have one, will be connected to those ports, right? But after that, we don't know anything. So we know that if you issue this out instruction, and I just wanted to go back to like slightly higher level view of this. Where is it? So when you say, look, I want to use port number 1F2, we know that this is connected to the disk. That's the only thing we know. After that, it's up to us to implement those instructions to make sure that we issue a specific read command to the disk. And the logic of the disk controller says, okay, as long as you say in this specific order, say output, like tell me how many sectors you want to read. So it's 1, and you put it in the port 1F2. Tell me the address from which you want to read. So it's offset. And by the way, there's I think with 8 by 8, it's a byte long addresses. So we split offset into 4 different chunks, right? So like offset's shifted by 8, offset shifted by 16, and offset shifted by 24, right? And we say, look, use ports 1F3, 1F4, 1F5, 1F6. And after that, you issue a specific command to the port 1F7, command 20, which probably reads read sectors, right? According to that's the only thing we have, right? But you ask a question like you say, can we assume that something else is there? So where does this else can come from? It's possible. You can say, look, maybe we rely on the Intel management engine to load something into memory of the machine and implement those read sectors routines, right? For us, that's okay. We can come up with the specification like that. But typically, people just simplify everything as much as possible and give you the control. Maybe you don't even have the disk and you don't even use the disk in your boot logic. You just go directly to the network interface, and then it's a whole different story, right? So, but that's everything what's happening, right? Does this answer your question? So it's not the system call. You build it yourself. Yeah, it's like literally if you take some other embedded class, you say, I have a microcontroller, there's nothing else, but I know that if I write into some port, it will like read me a sensor or something. Not much, not more than this, essentially. You just, this comes from, I put it online, but it's IDE specification. So essentially the port commands, right? But nothing, not much, not more than that. Okay, it makes sense. So we use this low-level function which reads a sector in a loop to read the L file into memory, and that's kind of powerful because you say, look, I never thought that I can access disk, but it looks really, really simple. It's actually very, very slow as well. And like later on, if you really want to, like there are better standards which allow you to access the disk faster, and real device drivers and real operating systems will use those other protocols. So this is kind of a prehistoric slow protocol which allows you to read some number of sectors, but in a slow manner, but without much effort. Question in the back first. Not really. So the high level design decision, and again, that's a good question. The high level design decision is that semantically the bootloader and the kernel are separate. The way I explain it, I kind of maybe kind of mix them together, but even in this implementation, you technically speaking can use this boot block to boot any other OS, not any other, but some OS, right? So because literally what it does, it says, I read ELF from disk and just jump to the entry point. That's what you do. And that's powerful. In practice, when you have something like grub on Linux, the 512 bytes will contain the first stage of grub. And then the first stage will read the second stage because the second stage is big, kind of like a kernel. It reads itself into memory. And then it says, okay, and now I can access all sorts of file systems. Boot, for example, Windows kernel, because I know which protocol Windows kernel implements, because it implements slightly different boot protocol. Or what is boot protocol? Like a convention between the bootloader and the kernel. And here the convention is very simple, almost non-existent. Just jump into the ELF file. And you can ask the second question, okay, but literally, why not to just have the kernel? The answer is that the BIOS, the standard with the BIOS says that it will only read 512 bytes. The rest will not be read. So the kernel is larger. There was another question. Correct. Right. So the next protocol will be SATA, serial ATA. What is ATA? I forgot. It's harder because we can probably talk about it later, but really here you can observe that you're reading one sector at a time, or maybe you're reading multiple, but you issue one command at a time. Meaning that somewhere around here, when you inside this wait function, you wait for the request to be completed, right? And for a spinning disk, it takes 10 million milliseconds, roughly one millisecond, which is roughly like whatever, 2 million cycles, or even like maybe 10 milliseconds, which is 20 million cycles to complete. So you're spinning here for 20 million cycles. The programs which we've seen in this class and all your homework probably finishes in like thousands of cycles. And we're sitting here for 2 million of cycles doing nothing. So it's obviously not efficient. And so those additional like better interfaces like serial ATA, they allow you to have like submit an array of requests. And actually requests can contain something what is called scatter gather lists. So meaning that you can like read multiple chunks of data and you submit them in like kind of in a synchronous manner, and there will be ring buffers to submit something and call for completion, and everything is kind of like asynchronous, just to make sure that you minimize this wait time. And NVMe protocols are even more efficient. They are more like network interfaces. They just submit a bunch of stuff and come back, and despite the fact that NVMe is like thousands of times faster than serial ATA and spinning disks, it's still, the protocol is arguably actually like same complexity, but like it's, you probably can build it. You can probably even fit it into like 512, but then it's harder to explain, I guess. So, but we can come back and look at the disk driver of the like a fast, which uses the faster implementation to access the disk. So it's not like by far much more complex, but it's slightly more complex. Any other questions? Okay, so we read the disk, we built this environment ourselves, no system calls, like you said. It's a good question, by the way, to clarify that this is nothing is available. I mean, we are who will build the system calls, right, later on. And let me switch back to the slide deck. And I hope this is what's shared. Okay, cool. So we read the sectors, we wait for the request to complete, but at the end, like what we're doing here, and again, the reason this homework is assigned is for you to like implement this loop, right? So essentially what happens here, it's exactly what's in the homework. So we say, look, we have a program header. We have entries in the program header. It's an ELF file, so we will be looping for the number of entries in the program header, and we'll be reading them from disk, right? And essentially, we read them one by one, and we assume that everything is compiled correctly, and we read them exactly into that physical memory location where the program is requesting to be, right? And by the end of this loop, what we're going to do is that we say, look, we believe that the ELF is legit and it has a legit entry point. So we will say just, okay, we create a function pointer. This entry variable is a function pointer in C. Do we know what function pointers are? It's just like you can have a pointer to a data on a heap, but C allows you to declare a pointer to a function. With this signature, which returns a void value and takes a void argument, meaning no arguments and no return values. And then in the next line, we immediately call this entry point, right? So we just go into the ELF which we loaded. Make sense? Question? Yeah, that's what we're doing. So this. Say again?
One segment by one segment.
Right, because ELF is a complicated format, right? So it's flexible enough. Like, okay, let me, like, the only static thing about the ELF is the header. So it's always at the beginning of the ELF file. From the header, there will be a pointer somewhere inside the ELF file, which will contain the program header table. This will contain some number of entries. Like it can be, for example, multiple text sections, or it can have a mix of text and a data sections, right? And so essentially those guys are pointers to further down in the ELF file. Everything is a pointer here. And the thing which happens is you might have an ELF file with multiple text sections, right? And then which are, I mean, we don't know what the person who compiled the ELF might request something funky. And so essentially those things will be said, okay, like error 1 and error 2, and we say we just will, like, we follow the protocol. We say, look, we will follow this table and load those guys in memory locations, like at error 1, and maybe if this one wants to be at error 2, we will just simply do this, right? Agree? So ELF is not like just a chunk of continuous bytes. It's like, this is what we do in a homework. And if you missed it, so maybe just try to revisit it. This is the organization. The header is static, always starts at the beginning. The program header table typically follows the header, but it can be anywhere. And those sections can literally be anywhere in the ELF file. There is no like any agreement on where they should be, out of order or anything. Anything is possible. And that's what we're doing here. Make sense? If I ask you, what is this line doing? Line 9240. Any guess what it does? Well, even from the names, we can say, look, if the program header memory size is larger than the program header file size, then what? Then this one sets. Yeah, you have a guess. Correct. So we're padding those with zeros. Like this is, for example, this section. Remember, we can have this BSS section, and we say, look, on disk we only contain so much bytes. Load them in memory. But the ELF says, okay, but actually the whole section is bigger, and you pad those with zeros. And so if you don't do this, then your variables will not be initialized to zeros. So that's what they're doing here. Like a minor detail, but I recommend you to pay attention to those details. Any other questions about jumping to the entry point of the L file here? All good? Okay, so, we'll look through this. And this is how our world looks like. We said, okay, we executed the code in the boot block, which was sitting here at 7C00. We loaded the kernel in memory. And I kind of say that the kernel was loaded at this address, which is specifically the first megabyte. And again, the reason we use this address is because BIOS and other like devices use this memory under the first megabyte to communicate with hardware. So this memory is taken. So we cannot load the kernel here. And we're essentially picking the first address, which is available on PC machines, and which is the first megabyte, and loaded the kernel into physical memory here. That's our kernel. It sits there in physical memory. And since we use the 0 basis for the segment, base equals to 0, this kernel is available at the same address in our logical address space, right? Or linear address space in logical addresses. Make sense? Okay, so nothing like really happened, and now we are executing at this, the program counter sits at the start, right? So this ELF entry point, instruction pointer is about to execute the very first instruction in the kernel. And the very first instruction in the kernel is effectively this. So essentially, it's also the kernel, it's x86 source code, entry.s, it's part of the kernel now, not the bootloader. And like this is the very first instruction which the CPU will execute. And you can ask yourself a question. Okay, let's get to that better. Let's get back to this a little later. So what we start doing here, again, our plan here is to eventually enable some kind of a page table, because in the end, we will be running with page tables. Right now, we say we don't really care that much like which page table we're going to be running. We just want some. But it has like a couple of specific things need to happen for us. We say, look, first of all, we will be using 4 megabyte pages instead of fine-grained 4 kilobyte pages. And we'll switch to a page table which uses 4 kilobytes later. But for now, during the boot stage in the kernel, we say 4 megabyte pages is just good enough. So these 3 instructions essentially enable 4 megabyte page extension by using this CR4 register and just like updating a specific bit in this register. That's fine, right? And at this point, our page table is very, very simple. We are just simply using an array which is of 1024 entries. Each entry is 4 bytes, right? And this array is a total of 4 kilobytes. And if you want to be more concrete, we're just using this array, right? So we load it in the CR3 register. On Intel, CR3 holds the root of the page table. And that's exactly what we're doing here. We say, look, entry page directory is our array. We're going to do some conversion on the address. And at a high level, what's happening here, we're converting from virtual to physical addresses, because inside the CR3, we need to have a physical address, right? And this entry page directory is actually a virtual address. So we will convert it to physical and then load it in CR3. And after that, like really, we can start using the page tables, right? So after loading it. So one interesting detail which happens during the boot, which is a little subtle, because in practice, there is no really strict need to do this, but nevertheless, we're doing. Our goal, when we start running processes, we want the process address space to start from address 0. Some process text will be linked and loaded to run at address 0. On top of that text section, we'll have some global variables, data section, then a tiny page for a process stack, then the process heap, which will be growing towards the top of the address space. And the way we want the address space to be split, we say like, look, we will reserve the low 2 gigabytes for the user access and the upper 2 gigabytes for the kernel. And obviously, the user cannot access the kernel memory, so we will set up the protection bits in such a manner that those accesses are not allowed, but the kernel is mapped to run here. And this area will be used for, like, roughly speaking, kernel heap. Let's put it this way. However, as we said, like, instead of like loading the kernel into physical memory at the second gigabyte, or like more specifically, second gigabyte maybe plus 1 megabyte, we literally just loaded the kernel here at the very first megabyte. So if this is our physical memory starting from 0, we loaded it right here, right? Why can't we load it in the like exactly second gigabyte? Why haven't we done this? Because in the end, we want the kernel to show up above the second gigabyte, because the first 2 gigabytes will be reserved for the user, right? So, but for whatever reason, in physical memory, the kernel sits here at the address, which is the first megabyte right now. Why can't we immediately load the kernel here?
Because
Typically, physical memory is continuous. There are sometimes gaps on modern machines, but let's not talk about those. But what's the real question here? Or real reason?
we load it with physical actions, so can't really assume there's more.
Correct. What you're saying is that x86 makes a pessimistic assumption that some amount of memory is available, but this amount may be lower than 2 gigabytes, right? And specifically, like, it depends. So if you boot on a machine which has like 4 gigabytes of physical memory, just go load it right here and everything will work. But, well, in practice, like, to do that cleanly, you really have to query the BIOS and ask a question, how much physical memory is available on the machine. And it's not very hard. So typically in the kernel, which we built with my students, we usually do this because otherwise it's kind of ugly. But x86 just blindly assumes some amount of physical memory. I think it's roughly 235 megabytes or something. And this is how the QEMU emulator is configured. That's why we say, look, if you try to load something here above this 235 megabytes, you will immediately get an exception and nothing will happen, right? So that's why they say, look, we just, instead of querying the BIOS, because it's a little complicated, but probably it's actually not that complicated, so it's probably would be a good technique, would be a good kind of style to do this. They just say, okay, the kernel is reasonably small, just maybe a 1 megabyte. So if we load it at the first megabyte, we just assume that the second megabyte is available, right? So that's why we load it in the lower addresses of physical memory.
So then what happens?
No, but hold on. It's not like you can manufacture physical memory out of nowhere. You're booting on a machine which has some amount. Maybe it's 16, maybe 32, right? In a modern world, it's like 32 gigabytes, right? But in a days, like, what you need to understand that there is some amount of physical memory, and it's like a finite resource. Like, think of those chairs in the room, right? So I can only sit so many students in this room, right? And I say, look, I come into this room before you, which never happens, but let's assume for a second. And I say that I have 20 TAs, and I say I will reserve the first row of 20 seats for the TAs, right? And so this is what, and I assume that those 20 seats are available. And after that, I will be dynamically managing the seats in the room, and I will have some kind of a seat allocator, and we'll see how x86 kernel will be managing physical memory, which is kind of similar to seats in the room when you request a new seat, right? So I don't know if I confused you with this analogy, but like you get what you get. Like, you have a machine with some amount of memory. Your goal is to boot, right? So maybe it's 16. So you cannot use anything above 16 here. And you carefully say, look, I will load the kernel above the first megabyte, and we'll use the rest, whatever 7 or 8 megabytes which are left, or not 8, maybe like literally maybe 14, to run user processes, which is still plenty, to be honest, right? Make sense? Or what was the question? Does it answer it? Kind of, okay. Okay, any other questions? So another one. Why did we leave the first megabyte, right? This memory, we will see in this next homework, is kind of similar to these in and out ports. If you write into the memory below the first megabytes, the way the hardware works, that instead of going to physical memory, it actually goes to devices. So for example, it can go to the graphic card. So in our homework, the homework will be asking you to print hello world on the screen. And the most basic way to print letters on the screen, there is like a low-level protocol that there is an area here starting from specific address, I forgot which one, and you write those ASCII characters, which hardware internally, you write a number, but it converts them into like pixels, which represent the letter H, and then letter E for hello, right, and so on. So it's done by the hardware itself. You just write the number, OX, some kind of a byte. But internally, the table says, okay, look, it will be looking at as those pixels on the screen, right? So this area of physical memory and some area at the very top of the address space is reserved by the BIOS to implement this communication with hardware. So it's kind of magical. And so if you just like allocate it for the user and operating system, then like some crazy stuff starts happening. You can try and see how it crashes. It will crash differently on real hardware, on QEMU, because QEMU emulates slightly differently, right? But and the reason is that like, for example, this area which I was mentioning, it's kind of like a frame buffer, right? So you've heard people who do graphics, they know that efficient way to communicate with graphical user interfaces or GPU device. Okay, GPUs are different, but they'd say VGA cards. That's a standard virtual graphical something, I forgot. So they implement a frame buffer. So essentially, you write the data in the frame buffer, the hardware scans the frame buffer and puts it on real physical screen for you. And I mean, again, like when I was your age, I was working on like video game engines, some naive ones, but essentially like Quake style shooters, right? And that was the thing. So we didn't have GPUs back then. So we like write everything what you want to render to be on the screen into this frame buffer, and then it shows up and you run through the through the whole sort of the labyrinth. But good question. Any other questions? Okay, good. So so hold on. So I started with this and I said, okay, we want the kernel to show up at the higher addresses. So how do we do this? Like it's physically here in the low addresses of memory, of physical memory. How do we make it to show up here? What is the mechanism we're using? Page tables, right? So don't be like that kind of cautious, right? So it's good that you know and you follow the class. Okay, we use page tables. Page tables will, remember, we talked about it. They kind of like this kind of a cloud. You take a virtual address and it says, okay, where do you want it to be mapped? And you say, look, I want it to be mapped here. So you will set up the page table in such a manner that, more specifically, let me show you the drawing here, that two regions of virtual memory from 0 to 4 megabytes and from the second gigabyte from 4 to 4 megabytes. So the size of those it's the same 4 megabytes. It just drawing is not up to scale. The size is the same, 4 megabytes. These two regions will be mapped to the first 4 megabytes of physical memory, right? So this means that in virtual address space, this address will show up twice. So it show up here at the first megabyte, and it will show up exactly here at the second gigabyte plus 1 megabyte, right? Does it make sense that we can do it? I mean, we control the page table at this point. Whatever we put in a page table will control the layout of the virtual address space. We don't do anything with the linear address space. We can do the same trick with the linear address space, but we don't want it. So linear address space just stays from 0 to 4 gigabytes, but the page tables will be configured to map this region of physical memory twice. Make sense? And specifically, just to give you an intuition, this is where we want the kernel to be, right? When I was showing you this diagram here saying that the kernel has to be at the second half of the address space, exactly at 2 gigabytes, or more specifically at 2 gigabytes plus 1 megabyte, this is why we have this second region. Make sense? Why do you think we need this first region? Why do we map it twice? Not exactly. So it's kind of fuzzy, but let's just be more specific. So I will ask you differently. What will fail if we don't do this? If we just say, look, since we want the kernel to be here at the second gigabyte, forget even about mapping this lowest part. Let me explain. Let's go, first of all, let's go instruction by instruction. Let's how do we enable the paging? And again, maybe the slides are slightly torn apart, so let's just very quickly go back to the source code to just verify. So I'm going to the entry.s. That's exactly what I was showing on the screen, and that's exactly what's running here. So at the end, we will jump to the main function, line 65. This is the entry where we started. We're just literally executing 3 instructions to enable 4 megabyte page table extensions. Then we load the page table into the CR3, and then we enable the paging with, again, setting the bit in the CR0 register, saying, okay, now use page translation, right? So I'll ask you a question. When you execute this instruction, line 56, this one, which essentially kicks in the paging, at what address the instruction pointer points? Guess the range. Correct, because this is where we were running, right? So we started at the first megabyte where we loaded the kernel in physical memory. Let me just quickly switch back to the slide deck to illustrate it. Leave from the current slide. So what I'm trying to explain here is the following. Let me just go here. Clean everything on this slide. Really? Erase? Oh, well, I cannot erase anymore. Hey, slideshow. Control-Z, just hold on, I have to erase everything. But what I wanted to explain is the following. So if you're about to enable page tables, right? No magic happens. So your instruction pointer is somewhere here, right? So literally speaking, it's here because the instruction pointer is the subject of segmentation, right? So segmentation doesn't change it. So it hits the physical memory at around here, which means that it's somewhere on my diagram here it's at 1 megabyte plus this plus 0x18, right? And suddenly we enable paging, which means that this address space is on. If we don't put anything here, if this one is not mapped, we immediately crash here with a page hole, right? Because translation fails. If this is an empty hole, this region doesn't exist. Instruction pointer may be moved by 4 bytes or whatever the size of this instruction, maybe it's 1 byte. You immediately page fault here. Does it make sense? So it's not atomic. And this is exactly what you said. So for just a little bit, we need to keep executing in virtual addresses, which are still here. And when we jump to main, I say that we jump to higher addresses. And at this point, we say, look, we no longer need this mapping. We can throw it away. Make sense? Like this argument that we will crash because it's like instruction pointer advances when you effectively when you say, look, I literally like I executed this instruction, this move, it enabled paging. This next instruction will be fetching from the whatever the size of this instruction plus 4, let's say, right? And this address is still in around first megabyte. And without a mapping, it will fail, right? Make sense? Kind of. Okay, good. Any questions about it? I see some confused eyes, so go ahead, ask questions. Correct. Correct.
So what's your
Correct, right? Because this table which we loaded, like this is the root of the page table, it will be used. The next instruction after this one will be, all the addresses will be forced through this translation, correct? And if you suddenly didn't configure the page table in such a manner that it allows you to even execute this instruction, then it's your fault. You will not boot. Make sense? Okay, wanted those level of details. And this is where we jump to the addresses which are above the 2nd gigabyte. And you might ask a question like who controls this? How do we even force the kernel to be linked in to run in those addresses, right? And just to make sure that we understand that, okay, this is really, those are really the addresses which are used. Let me illustrate. So objdump, the tool, which I was advertising in previous lectures. And if we say, okay, show us the symbols, grab for sim, and it says, okay, display the symbol table. So it's all the symbols, all the global and local and everything. Local is probably not, but global variables. So we do objdump, objdump minus sim on the kernel and this one. Oh, actually, I did make clean, so we have to make the kernel again. Just a sec. Let's quickly make x6. Let's do this. Objdump minus sim on the kernel. And like you may ask a question like, how do I know that this is really the kernel? I read the makefile, and I recommend you to read the makefile, and you will see that this is the kernel. And you say, look, and then I will grab for the main. Well, it shows the main to be like, really? Just wanted to. It shows the main to be at this address. Like, and if you do Python, do I have Python? Really? What Python do I have? Sorry, why is it so slow? Not sure. So if I take this address of main symbol and like put it in Python, and just to make sure that it translates back to decimal, it's a 2nd gigabyte, right? So it just verified that the main is linked to be at the 2nd gigabyte, right? You might ask a question, so how do we control where those addresses are, where the kernel is linked at? So who can make a guess how we do this? Remember, relocation, linking, loading. So which tool in the tool chain make sure that we relocate the program or link the program to run at a specific address? Do we remember? Yeah, correct. So you will ask the linker to use this to link the kernel at a specific address. If you look at the makefile and you say kernel, there will be multiple. So this is the kernel target, and you say, look, okay, I see that we are building the kernel right at this line. So this is the invocation of the linker. We use this object files and we do different things. But instead of giving the flag to the linker, although it's possible, as you said, the authors of x86 use a linker script. And if we go and read this linker script, kernel.ld, what is it? What do I do? Vim, edit. It's a specific format which the linker understands. And I'm not asking you to like deeply understand what's going on here, but roughly speaking, you can tell the linker, okay, I want a text section at a specific address. I want a data section, read-only data section right above it, and so and so. And by the way, I want at the very end of the kernel, the PSS is here, at the very end of the kernel, the linker will actually insert this AND symbol. We will use this AND symbol later because we want to know where the kernel ends in memory, and we will be able to access it. Like it says, okay, provide the end of the entire thing here. End of data is here. End of e-data. Not exactly sure, like end of data is here. And what specifically we're doing in this linker script, we say, look, and this is the format. You say, please link the kernel to run at the 2nd gigabyte plus 1 megabyte. I just wanted to make sure that we understand those details because, again, the devil is in the details. And I understand that, okay, conceptually, it's very easy to say, okay, be linked at this address and everything will be happy. But imagine tomorrow you show up for work and someone asks you, okay, can you quickly build us a kernel which will boot on this specific architecture? So you need to know at least some bits of the tool chain. And they're not hard. They're like just confusing, honestly. And I don't know the details myself. So every time if you ask me to do this, I know where to start. I will start looking at this. But then if I want, I have to read specifically the language of the linker. But typically you don't have to, right? So, okay, this is where we say, please start at this address at 2nd gigabyte plus 1 megabyte. So if you do the Python thing again, on this address, so it will show you, it will show you that it's exactly, that's the true like 2 gigabytes plus 1 megabyte address. Doesn't look pretty, but it is. Okay, cool. So any questions about it? So essentially we say the whole kernel, all the data sections in the kernel and everything, like the main function is, sorry, let me restart the current slide, restart the slideshow. All the data, all the global variables, everything is linked to be at this virtual address range. So when you use like any variable in a kernel, like entry, page, dir, which we use, or main function, they will be somewhere here, right? That's why we prepped everything to get the kernel running at this address. Even before we started loading, we just compile it to be there. And now we just make sure that we temporarily enable this region of addresses just to make a switch, because we were still executing at this lower addresses. And the moment we say call of the main function, this is where the IP instruction pointer switches to the higher addresses, right? And after that, okay, so like a lot of interesting details. We say, by the way, we were using this kind of like dodgy stack in the past. Let's instead like have our own stack, because we can control the size. In practice, x86 still sets it to 4 kilobytes. It's actually like it's a good size, 4 kilobytes. That's fine. You can change this number; it will work. But essentially, it's just in assembly they declare a variable which is 4096 bytes, and you switch the stack to be at the end of this array. So making sure that you're no longer using this this scratch space below the 7C00, but really use the stack which is compiled to be right here, right? This is where the stack variable is located in the data section of the kernel. And after that, you're good to go, and you say, look, fine. Instead of like, oh man, my pen died right here. Instead of just invoking it like a call instruction, you load this symbol into the EAX register and jump in directly. So essentially, you jump to this address. The reason for that is that you simply leave this assembly as a call of a main address. The assembler or the compiler, specifically assembler in this case, will generate a PC relative address because it says, okay, we believe that you were like it's a local variable. We don't have to like link and load anything later on. So just let's do a relative jump. And we don't want to do this. So it's just a trick to avoid it. And essentially jumping to a specific address in the main kernel. And after that, you immediately find yourself running right here in the main function of the kernel. So essentially your mission accomplished. You're inside main, C is around you. You don't have to worry about assembler much anymore. And life is easier, right? So in the homework assignment, which you will get later, probably today or tomorrow, will ask you to boot into main in a similar manner, essentially. Just make sure that you can reach the main. So essentially stitch everything together and make sure that you can reach main function. Any questions? Boot it into main. Everyone is tired. Okay, then I will have questions, and well, that's my poll. Time for the poll. Let's verify our understanding of everything. This diagram actually, it shows you everything what kind of happened in one single drawing. Let me switch to the poll everywhere real quick here. Okay, so that's my very first question. So in my very first question, which you can find online, I'm asking which ranges of virtual addresses are mapped when we reach the main function. So and you should pick the ranges which you believe are mapped. There might be multiple. I'll wait for a little bit. In fact, I might want to present it. Just a sec. What are you saying? Let me show. Let's just stare at those and say again. No multiple choice. Really, the way the activity is set up. Let me for a second. What is this? That's different. Let me for a second enable multiple choice for a sec, just to hide the answers for a second. Go to this thingy. Side response setting. Are you sure that multiple choice are not enabled? Really? But why? So can you try to click multiple answers now and see if it works? It doesn't? Not published? Activate again. Okay, yeah, published again. So maybe change your answers. Okay, so now it works. And still not sure honestly, which option. Like this is what I have on the screen. Like go figure. So which one of these you think controls multiple choice sensors? Who is doing HCI in this room? Like human computer interaction. A lot of people kind of like say, okay, the discipline is solved, doesn't make sense. But in practice, this is a good example of HCI. Like I cannot figure out which of this enables multiple choice. Probably one of these two, but which one? Okay, probably this one. Each person may, no, I don't honestly know. So which one of these? Your guess. But again, at this point, I see that people are converging to the right answer. So like correct. So 0 to 4 megabyte and 2 gigabytes to 2 gigabytes plus 4 megabytes are the two regions which are mapped. Agree on this? And that's because it's exactly on this screen. So this is the virtual addresses. So we map from 0 to 4 megabytes and from 2 GBs to 2 GBs plus 4 megabytes, right? Okay, cool. We understood this. Let's move to the next question. Everyone in the room answered, so I don't have to like patch the answers later on. Yes? Last call. Okay, cool. So let's try the next one. So hopefully that one is deactivated. This is activated. So what I'm asking here is at which physical address the kernel binary is loaded or located. Physical address, guys, physical. Don't forget, this is the diagram. So you still can change the answers, right? This activity, right? So who are those people who like, okay, do we still have a, it seems that people are a little confused, and some people, like 22% of people right now, saying that the kernel is mapped at physical addresses where the kernel is located as 2 gigabytes plus 1 megabyte. Is there anyone in the room who thinks so, and why? Because, like again, let me try to explain. I kind of like it's probably fun, like to, if you are in the room, right? So you can look at this picture, and you say, look, like in virtual addresses, the kernel is here and here. It's double mapped. But in physical addresses, it's just here, right? And this is where we loaded it. And this magical value is 1 megabyte, right? So it doesn't show up here at 2nd gigabyte, right? Just because this physical memory may not even be available, right? Make sense? Okay, so hopefully everyone correctly changes the answer. So the number of people like in the room, everyone answered? Good. Okay, cool. Let's go to the next one. That's another simple question, but hopefully at least a little helpful to understand everything. So I apologize. At which virtual addresses the kernel binary is mapped? Select all. And again, probably I didn't allow you to choose multiple. Okay, let me, if I edit. So can you now choose multiple? Not yet. Okay, so deactivate for a second, just a sec. Let's edit it again. Oh, I don't know. I will do this. I'm not sure how it's supposed to work. Honestly. Save. I'm clicking save multiple times already. Well, at this point, even the website doesn't work for all everywhere. Let me double check one more time. Response settings. Okay, this one is not saved as many times as the one saved. Okay, is it active again? Oh, this is not active, right? Okay. I'm almost there. Apologize. Cancel. Multiple choice inactive. Okay, cool. So sorry, I apologize. Then yeah, cool. So then fix the answers, guys. So again, read the question carefully. But what is active? It's okay, got it. Okay, which virtual addresses? So who can, like, at least who can tell me from the audience? So what is the correct answer? Correct. So these two, right? Because this is exactly what we have on the screen. Is it clear for everyone in the room? I mean, and this drawing is pretty accurate. Like the only minor detail which I screwed up on a drawing is that this one and this one are not the same size. So they should be like they should be, it's not to scale, right? So, but the kernel shows up twice. It's mapped here at first megabyte 1-to-1, and it's mapped here at 2 GB plus 1 MB, just because we remapped the same physical memory twice, right? Make sense? Everyone is on board? And okay, now the last final, the killer question, which is the most challenging, but it's not graded. But if I understand correctly, what I'm asking here, and I don't have good experience with those activities, it asks you to correctly sort the steps of the boot protocol. So essentially, we were talking about it for a while, and now try to go ahead and figure out how to build it. And what do I have here? Oh, sorry. Like if I switch back to this screen, say present, let's take a look at what people are thinking. And I don't know how this activity works, but can you just drag it around? Does it work this way or not? Okay. But then do I see the final answer from everyone, or you have to submit first? Oh, okay, people started submitting. Okay, cool. Let's do it. Let's design our boot protocol real quick. Make sure that we understand how it works. Majority of people answered? Not yet? We can, like, it's only like 2 minutes in this class, but just 1 minute left. Let's discuss the answer. Okay, let's like, again, here I just grade participation. So like submit some answer just to make sure that everyone in the room submits something. So let's take a look at the screen. So people say we initialize temporary stack at 7C00 as the first step. That can be correct because it doesn't matter. But in practice, x86 actually first does the GDT setup as like the first and second step of flipped, but it doesn't matter. You can do either first. It's just that logically you first do the GDT and then right about when you call the boot main function, which loads the kernel from disk, the C function, you set up the stack. But you guys are correct. Then yes, you load the kernel from disk into memory. here you actually have to jump to the entry point of the kernel after you load it, right? So I'm not sure why you decided that you have to enable 4 megabyte page extensions, because remember, I was trying to advocate for the semantic split between the bootloader and the kernel. The bootloader just puts the kernel in memory and leaves it there with segmentation enabled, right? And after that, the kernel can do whatever it wants. And this logic of enabling 4 megabyte page extensions is done inside the kernel, right? And okay, we enable the 4 megabyte page table extensions, load the page table route into the CR3 register, switch to the kernel stack, and jump to the main. So yeah, more or less you guys are correct, which is kind of good. The conclusion here that I assume that most people will be able to essentially finish the homework, which asks you to boot into main. Which is not that hard, actually, especially since we discussed everything twice, and hopefully, it's fun as well. So I'll stop here, and then on Thursday, we will continue designing and building the kernel from inside the main function.